We generally encounter helium in moments of celebration. It is a triviality of childhood, a gas that makes decorations float and voices squeak for a few hours before the party ends. When balloons slip from a child's hand, they carry a substance defying Earth's gravity, drifting toward the stellar environment where it was first forged. In 1868, astronomers turned their telescopes toward a solar eclipse to analyze the sun's chemical makeup. Within the spectra of light, they found a specific yellow line, a frequency that did not match any element known to exist on our planet. The observation confirmed a new addition to the periodic table, one found 93 million miles away before it was ever touched by human hands. They named it after Helios, the Greek god of the sun. For the next 3 decades, helium remained a laboratory ghost, an element that existed in the stars but remained missing from the Earth's own crust. This history frames our current use of the gas. We are handling the first element discovered in the heavens before it was found on the ground, treating a cosmic rarity as a disposable toy. Most of the universe's helium is the product of stellar furnaces, the result of extreme physics occurring in the hearts of stars like our sun. This is nuclear fusion. Under immense pressure, hydrogen atoms collide and merge to form a heavier helium nucleus. This reaction releases energy that sustains our solar system. The light reaching Earth today began with these atoms. While the sun fuses helium, the supply we find on Earth is created through a different, much slower process. Deep underground, heavy elements like uranium undergo radioactive decay, shutting alpha particles that eventually settle into helium atoms. This gas is so light that it continuously migrates upward through the Earth's crust. It only remains on our planet when it becomes trapped beneath impermeable layers of rock, often pooling alongside deposits of natural gas. Capturing this gas requires a massive industrial footprint. Because nature takes millions of years to generate even small amounts through decay, we must extract every available pocket from these ancient subterranean reservoirs. Once we deplete these pockets, they do not replenish on a human timescale. Every atom extracted is a finite piece of our planet's history. The industrial effort is driven by helium's unique physical profile. It is the only substance that can remain liquid at temperatures approaching absolute zero, making it the most effective coolant in existence. Modern medicine relies on this property to operate MRI scanners. The superconducting magnets inside these machines must be bathed in liquid helium to maintain the stable magnetic fields required for high-resolution imaging. Without this cooling, these magnets would overheat and fail. Millions of diagnoses, from detecting tumors to mapping brain activity, depend on this gas. In aerospace, helium provides the pressure necessary to keep fuel flowing into rocket engines. As fuel is consumed during launch, helium is pumped into the tanks to prevent them from buckling under atmospheric pressure. Its unreactive nature also makes it essential for manufacturing the microchips in our pockets and the quantum computers of the future. It provides the inert environment necessary to build our most delicate technologies. We have built a high-tech civilization that is fundamentally dependent on an unmakeable gas, even as we continue to use that same gas for entertainment. The utility of helium is limited by a specific physical constraint: its atomic weight. It's so light that it interacts with Earth differently than any other resource. Earth's gravity holds oxygen, but is too weak to retain helium. Once in the open air, it begins a one-way journey upward, crossing the upper atmosphere and bleeding into the vacuum of space. Unlike water, no natural cycle returns it to the ground. This creates an economic tipping point. Every vented MRI, every launched rocket, and every released balloon represents a portion of the global supply that is gone forever. As the demand for advanced medical and computing technology grows, our underground reserves are dropping. We are consuming a resource that requires geological eras to accumulate in a matter of decades. We are siphoning a supply that we cannot replace, drifting toward a future where our advanced tools may lack the element required to run them. Helium serves as a reminder of our connection to the wider universe. Whether forged in a star or born from the slow decay of the Earth's crust, it is a visitor that our planet cannot keep. So the next time you see a floating balloon, Remember, you are looking at a literal piece of a star.